This is my linear to rotational motion extra credit project with my topic being the piston crankshaft mechanism. We can differentiate types of motion by considering the manner in which the motion occurs. Linear motion is associated with an object moving in a straight line. Here, any point on the object undergoes the same straight line motion as any other point on the object. The units for linear motion is length per unit time and time squared for velocity and acceleration, respectively. Rotational motion is associated with an object spinning or rotating about an axis or a fixed point. Here, the axis of rotation of the object, or in this case point P, does not translate from one point to another. Instead, point P stays in the same location and all of the points on the object spin with the same rotational velocity or acceleration, but different linear velocities or accelerations, depending on how far the point is from point P. The units for rotational motion is change in angle per unit time and time squared for angular velocity and angular acceleration, respectively. Our system converts the linear motion of the piston to the rotational motion of the crankshaft. The piston crankshaft mechanism is an essential mechanism for engine operation. This mechanism connects to the transmission, which ultimately causes the rotation of the tires. Inside the engine, there are pistons which are connected to the crankshaft by connecting rods. Let's get a closer look at how these connections are formed and operate under motion. As we can see here, the small end of the connecting rod is attached to the piston using a wrist pin, which allows the connecting rod to oscillate well within its full range when the piston moves downwards. A more detailed representation of the assembly is shown here. A needle sleeve bearing is placed in between the walls of the short arm's circular portion and the wrist pin. This bearing has many long cylindrical rollers resembling needles in order to reduce friction along the rotating surface. Circlips are placed at the ends of the wrist pin inside of the piston in order to prevent axial motion of the wrist pin while permitting rotational motion. Towards the big end of the connecting rod, there are bolts and nuts that keep the bearing inserts fitted around the crank pin. These bearing inserts allow for smooth oscillations between the bearing inserts and the crank pin. The crank pin connects the big end of the connecting rod to the rod journal, which allows for the rotational motion of the crankshaft. The motion that these components undergo are shown in this video, where the connecting rod can transfer motion from the linear motion of the piston to the rotational motion of the crankshaft. The first internal combustion engine was created in the late 19th century by Charles and James Duryea. This engine was a one-cylinder, 4-horsepower engine that went into the first working gasoline-powered automobile. This automobile was individually crafted for the economic elite, and only 13 were produced. Later on, Ransom Eli Olds created the first assembly line where the production time was greatly reduced. After the first assembly line and the first engine powered by gasoline, Henry Ford pushed for widespread production of his Model T, which enabled the Model T to be more available to the general public. Without these innovations in the internal combustion engine and its production, the piston crankshaft mechanism wouldn't be nearly as advanced as it is today. The pistons in an engine pass through a repetition of 4 strokes shown here: intake, compression, combustion, and exhaust. For our purposes, we will only concern ourselves with the combustion part of this process, since this is where the relevant work is done on the crankshaft. The combustion or power stroke stage occurs when the pressurized air-fuel mixture is ignited, resulting in an explosion that pushes the piston downwards. This is what causes our linear motion. Each revolution of the crankshaft is complete after 2 piston strokes are complete. As we can see from this video of a Chevrolet 350 engine, The pistons in an engine have their strokes occur at different times in order to compensate for outer moments, minimize internal moments, and therefore reduce the amount of vibration and bearing stresses. Counterweights on the crankshaft serve this same purpose. Here are some basic linear and rotational equations applied to this mechanism. In Physics 1, these variables are determined through constant changes. In our applications, these changes can only be accurately modeled with more complex equations. Here I have the parameters of velocity, acceleration, angular velocity, and angular acceleration listed as functions of time, but each parameter here can be a function of many different parameters. We use these functions in order to obtain a more accurate model of any variable under analysis. We can explore general plane motion concepts and equations in order to apply similar concepts and equations to our mechanism. General plane motion describes an object that stays in the same plane for the duration of motion. We will be dealing with the scenario of both translational and rotational motion. We use relative velocities in order to find the velocity at any given point on the object. The relative velocity at point A describes the velocity at point A that you would see if you were standing at point B. Therefore, the equation for the velocity of A relative to B is the velocity at A minus the velocity at B. Now we introduce angular velocity. Angular velocity acts perpendicular to the plane, and since we are spinning about a translating z-axis at any given time, our angular velocity only acts in the z direction. In this figure of a rotating object about a fixed axis, we can take the cross product of the angular velocity about O and the position of A relative to O in order to obtain the velocity at point A. We apply this concept to our previous figure in order to obtain the equation for the velocity of A relative to B. And if we set the two equations for the velocity of A relative to B equal to each other, we obtain our final form of the equation, which we can use to analyze double rotations. Our example of a piston crankshaft mechanism is an example of a double rotation mechanism. From this image that I created from one of our PowerPoint examples, the piston, connected to the crankshaft by a wrist pin at point A, causes a velocity and acceleration down the piston's constraining walls. This causes an angular velocity and acceleration of the connecting rod about point A. Through the connection at B, the motion of the connecting rod causes an angular velocity and acceleration of the rod journal. The rod journal is connected to the crankshaft through the fixed axis crank pin, or point O. We can represent the linear velocity of point B at this instant as the linear velocity of point A plus the cross product between the angular velocity of the connecting rod AB and the position vector of A relative to B. We can represent the linear velocity of point O at this instant as the linear velocity of point B plus the cross product between the angular velocity of the rod journal BO and the position vector of B relative to O. In this case, the linear velocity of point O is 0 since the crankshaft is in fixed rotation. The same method applies for finding linear accelerations. Here, I listed a helpful video describing an alternate method of analyzing a double rotation system.